UCLA, where he'll be a rising junior this year. Suyash has been working with Andrew Emmerich over the summer, and he'll tell us about his project, metal mixing in simulated dwarf galaxies. Go ahead whenever you're ready.
Thank you for the introduction, Gwen, and I thank you all for attending the Student Symposium today, and I'm really excited to share my work for the summer, so let's dive right in. So when we're talking about galaxy evolution, there are sort of two facets to it. We have the chemical evolution of galaxies and the physical processes that drive them, which could be stellar evolution, mergers, and turbulence of galactic gas. But the more important and interesting question is how exactly these things relate. And that's exactly what the field of metal mixing deals with in discussing chemical evolution in galaxies and the driving forces thereof. And so a brief overview of everything that we need before we go into the study is that our current best shot are simulations because of a relative obscurity of observational data regarding metal mixing investigations. Previous studies have focused on chemical evolution in isolated dwarf galaxies because they are the simplest kind of galaxies to probe into and expect some clean physics to come out. And our target is to focus on metal mixing, which is a broader topic, for 3 simulated but non-isolated dwarf galaxies, which is different from isolated because isolated ones have already been dealt with. And our sample galaxies will have dark matter halo masses of 10 to the 10, 11, and 12 solar masses. And our hope is to find some models for metal mixing that are testable by observations, because that is the whole point of astronomy. And so we begin by finding a bridge between the chemical and the physical evolution of galaxies, a region called the neutral interstellar medium phase. So what I have here is the present day heat map of a simulated dwarf galaxy that has a dark matter halo mass of roughly 10 to the 12 solar masses. And the important point here is that the neutral ISM phase, which for your reference are the magenta regions in this figure here, house the star forming gas because they are essentially all the cold gas in the neutral, in the interstellar medium. Which means that we can expect some sort of correlation between the chemical evolution of the neutral ISM and the processes that could be driving it, particularly star formation, changes in dark matter halo mass, and turbulence of galactic gas. And so we begin our study with investigating the chemical evolution of the neutral ISM. And the way we'll do that would be by constructing abundance distributions and studying their evolution. And so as the first step, we would like to construct abundance distributions, and I'll walk you through it step by step, what these things are and how we make them. So once again, I have the present day heat map of a simulated dwarf galaxy that I showed to you right before. And we would begin with identifying regions that are part of the neutral ISM, which you can see are encircled here right now. And we then sample abundances and masses from these regions. So all of these regions would have some amount of metals and individual masses. Iron is being used as a proxy here for other metals for good reason, which I'll be happy to discuss in case you're interested. But nevertheless, we find the spatial distribution of the metal abundances, in this case iron, and the masses of these regions. And we go ahead to construct a histogram for these abundances, weighing by the mass distribution across the regions, which gives us something like this, a histogram. But we are actually interested in constructing a continuous envelope around this histogram, this blue line that you see here. And this blue line is exactly what we call abundance distributions. And the next job is to fit these abundance distributions. So previous works have performed analytic fits for isolated dwarf galaxies, but we wanted to try out the same models for non-isolated dwarf galaxies. And as you can see, the models fit pretty well. And now it's worth describing what these analytic models exactly are. So on the left half, we have the Gaussian functional form, and on the right, we have an exponential decay functional form. So the part of the distribution that's in the Gaussian represents gas that is well mixed. And the part of the distribution that's in exponential decay represents gas that is enriched or not well mixed. And the abundance where the functional form shifts from Gaussian to exponential decay is called the transition abundance. And so that completes the construction of abundance distributions, but we are also interested in their evolution. So sort of naively, we can look at an animation of how these distributions exactly evolve in time across all these galaxies. And that is exactly what I've portrayed here for the iron distributions in all three of my sample galaxies. And this is pleasing to look at, but not exactly very helpful because we need numbers for modeling evolution. And so we do an alternate approach by looking at abundance statistics, which are essentially some important parameters of the distribution. We do so by first realizing that the fits are predominantly Gaussian and therefore can be well summarized by their median and spread, which I have represented here. And instead of looking at the whole picture of the distribution, we can look at how the median and the spread evolve as a function of time instead. And so we go ahead and do exactly that. So here I've plotted the central tendency as a function of time for the iron distribution across all three sample galaxies. And the central tendency is an umbrella term for the mean, median, and the fitted parameter mu of the Gaussian. And the one thing that I request you to notice is that these plots are somehow reminiscent of charging capacitors, if you're aware of them, which gives us hope that we can model them analytically. And thereafter, we go ahead and plot the spreads as a function of time using two metrics for the same, the standard deviation of the distribution and the fitted parameter sigma of the Gaussian. And we do this for the iron distribution in all three sample galaxies. And I would like you to notice that these plots are again reminiscent of discharging capacitors, which also gives hope that they can be modeled analytically. And so we go ahead and try out our ansatz, trying to fit the median abundance and the abundance spread with exponential functions, and we succeed in doing that. And the essential physics behind this is that the producers of metals, which are essentially supernovae and control the median abundance, and the mixing agents of metals, which are essentially galactic winds and control the spread of metals, these are part of negative feedback systems, which naturally produce exponential functions. And I say new analytic model with a word of caution because this hasn't appeared in the limited amount of literature that I've read before, but because they appear across all three galaxies, we are definitely onto something here. I've only presented the model for the least massive galaxy because it generates the best fit, but I have the models for the other two if you're interested. And as we go ahead, I would like you to remember this plot for future reference. And with that, we complete the first step of our study. We have studied the chemical evolution of the neutral ISM and come up with an analytic model for it. And thereafter, we are interested in studying the physical processes that might be responsible for driving this chemical evolution of the neutral ISM. And we'll be looking at star formation rate, the dark matter halo mass, and the mean Mach number, which parameterizes turbulence. And so we begin with looking at the log of the star formation rate as a function of time. We look at the average star formation rates for different averaging periods, and I present to you the plot for the least massive galaxy here. And peaks in star formation essentially represent what we would call starbursts, and larger averaging periods produce smoother profiles, as you can see for the 1000 mega-year case. And that's because larger averaging periods are less sensitive to local disturbances in the galaxy temporarily. But the essential upshot is that there's no definite analytic prescription for the star formation rate as a function of time, which is why I've just presented to you one plot. And then we look at dark matter halo masses as a function of time. And we realize that the steep slopes in this plot essentially represent important events in the history of the galaxy, like mergers. But again, the upshot is that there's no specific analytic prescription that we could come up with for this plot. And that is why we have just presented to you just one plot for the least massive galaxy. I do have plots for the other two galaxies in case you're interested later. But something interesting happens when we plot the mean Mach number, both the mass and the volume weighted means, as a function of time. So for the more massive galaxies, we do not find good analytic descriptions. But for the least massive galaxy, when we make this plot, we realize that there is a linear description of the mean Mach number as a function of time. And this is also something I would like you to remember as we go into the final and the most interesting part, of our investigation, namely relating the chemical evolution of the neutral ISM and the physical processes that drive them. So at this point, we can do with a short recap, where you might remember this plot where we model the abundance statistics as a function of time for all galaxies. And you might remember this plot where we realized that the mean Mach number of the least massive galaxy has a linear description in time. And that means that we can model the abundance statistics as a function of the mean Mach number instead, for the least massive galaxy, of course. And I present to you this model for the iron distribution in the galaxy. And this is exactly what we call the turbulence-based abundance model. And this model is interesting because it's testable via observations, because if we can measure quantities on the X and the Y axis, we can test and improve these models. And if these models are legitimate, we can measure the mean Mach number and infer abundance statistics of the neutral ISM. And that is great because mean Mach number is a physical property that's relatively easier to observe, while abundance statistics are chemical properties that could be difficult to infer from observations directly. And so in summary, we studied the chemical evolution of the neutral ISM, coming up with an analytic model for the same. We studied the physical processes that drive them and realizing that there is a linear turbulence model for the least massive galaxy. And we came up with a metal mixing model, which models abundance as a function of the turbulence in the least massive galaxy. And going forward, we want to ask ourselves some important questions, namely, are the models that we came up with for the evolution of the neutral ISM retained for heavier galaxies like heavier dwarfs or Milky Way-like galaxies? And are there other important processes that we should directly incorporate into our analysis, like supernovae in the form of supernovae rates? And the most challenging question of all is to come up with new models that connect the star formation rate or supernovae rates to abundances. And this is a challenge because these physical quantities evolve somewhat chaotically in time, and there could be a time lag between when these physical events happen and when a response in the chemical composition of the galaxies is produced. But nevertheless, that is it for this summer. Thank you for your patience, and I would be happy to answer any questions.
Nice job, Suyash. Questions for Suyash?
Yeah, this is Coral. I have a question. Great job, Suyash.
Thank you.
So you said you want to look at heavier dwarfs. I'm interested in lighter dwarfs, and I know you used, these are Milky Way satellites, you said?
I'm not exactly sure of their exact location.
But they're near the Milky Way.
Right. So I actually am just aware of the masses of these galaxies. I'm not too sure of their location, but one thing is that the most massive galaxy in our data set that has a halo mass of roughly 10 to the 12 solar masses, it is a roughly Milky Way sized galaxy. So it hopefully provides a window into looking at Milky Way sized galaxies in the future.
Okay. Yeah, because with those simulations, I'm not sure you could, I mean, you can't really go lower mass, but if you, because the metal mixing has been done on the isolated dwarfs, but not your sort of Mach number abundance tests, I don't think. So it'd be interesting to apply those to some isolated dwarfs and maybe see where it breaks down on the low mass end.
Definitely, yeah, that should be a great idea, especially because isolated dwarfs have pretty much been studied only for the chemical evolution. So metal mixing might be a good topic to explore there as well. Thank you.
Great.
Other questions for Suyash? All right, very nice job.
Thank you.